So tonight we're going to be talking about pH and pOH. P what? Okay, so it's all about water. When we're talking about acids and bases, as we have been, it has primarily been broken down into a discussion about hydrogen ions and hydroxide ions, which make up water. So you've got liquid water, and that's made up of hydroxide ions and hydrogen ions. For the majority of the time, water exists with an equal concentration of both hydrogen ions and hydroxide ions, with the product of their concentrations being written as Kw is equal to the hydroxide ion concentration times the hydrogen ion concentration, which is going to be equal to 1.0 times 10 to the negative 14. So this is another constant that we have. You know, we've had KSP and KEQ. Well, Kw is the water constant, and it's talking about the ratio of the concentration of the products in this equilibrium reaction of hydrogen ions and hydroxide ions over the concentration of liquid water. But of course, liquid water cannot be written in the KEQ because it's a liquid. And that value, which is a constant, is 1.0 times 10 to the negative 14. So it's all about the hydroxide ion concentration. If a substance, when an acid or a base is made, it's made by dissolving a substance in water, which in turn dissolves the substance and makes it into ions. If a substance releases hydrogen ions, hydrogen ions or H plus ions, the solution is considered acidic, and the H plus ion concentration is greater than 1.0 times 10 to the negative 7, which would mean greater, meaning like 1.0 times 10 to the negative 6, negative 5, negative 4, negative 3, negative 2, negative 1. Because, remember, we're talking about negative exponents, so greater is actually the smaller number. If a substance releases OH minus ions, the solution is considered basic, and the H plus ion concentration is less than 1.0 times 10 to the negative 7 molar, so something like 1.0 times 10 to the negative 8, negative 9, negative 10, negative 11, negative 12, negative 13, and negative 14. Basic solutions are frequently referred to as alkaline solutions, and that's primarily because they are usually made up of the alkaline metals or alkaline earth metals. Okay? So let's simplify it with pH. So a scientist decided to investigate this, and his name was a pretty funny name. It's Soren Sorensen. But Soren Sorensen proposed a less bulky way to express the H plus ion concentration, and decided on a scale from 0 to 14, or the pH scale. Here, a pH of 7 is considered neutral, so that's right smack dab in the middle. A pH of 0 is very acidic, and a pH of 14 is very basic. The pH of a solution can be calculated by taking the negative log of the concentration of H plus ions. So pH is negative log of the hydrogen ion concentration, and that is what's going to get you that number between 0 and 14. So if you are an acidic solution, your pH is less than 7, and so your hydrogen ion concentration is greater than 1 times 10 to the negative 7. If you're neutral, your pH is 7, and your hydrogen ion concentration is 1.0 times 10 to the negative 7. And if you're basic, your pH is greater than 7, and your hydrogen ion concentration is less than 1.0 times 10 to the negative 7. So what does that mean about pOH? So pOH, or the pH of the hydroxide ion, is equal to the negative log of the hydroxide ion concentration, just like pH is the negative log of the hydrogen ion concentration. And this can be calculated actually using the hydrogen ion concentration using the following relationship. So if you don't have the hydroxide ion concentration, you can actually use the hydrogen ion concentration, because pH plus pOH is equal to 14. So it's all revolving around this number 14. Or pOH is equal to 14 minus negative pH, or 14 minus pH. Okay, so it's all relating to 14, and it's all about hydrogen ion concentration, or if you have it, hydroxide ion concentration. So if I have this scale, which has just a bunch of examples of acids and bases, going from HCl all the way down, like 1 molar HCl all the way down to 1 molar NaOH, you can get some neutral stuff in there like pure water, seawater is slightly basic, milk of magnesia, ammonia, tomato juice, all these things. If you actually look at the hydrogen ion concentration, you can determine the pH, because the negative sign, if your hydrogen ion concentration is 1.0 times 10 to the negative something, that negative something is your pH. Milk, having a hydrogen ion concentration of 1.0 times 10 to the negative 6, has a pH of 6. So it's kind of cool like that. But that only works if your concentration is 1.0. If the coefficient is not 1.0, then the pHs aren't always just the exponent. So in these instances, you can approximate the pH value given the concentration. So if you know that the concentration is 4.2 times 10 to the negative 10, we can assume that the pH is going to be somewhere between 9 and 10. If you take this, the pH is negative log of the concentration, you get a pH of 9.38. So closer to 9 than 10 because this number is closer to 1 than 10, or 9.99. So that's kind of how you can approximate. You could know where the pH is between without having to calculate it. When we're talking about sig figs, it's kind of weird, and don't freak out about it, but when writing the pH after calculating it from the concentration of H plus ions, to figure out the number of sig figs, you're just going to take the number of sig figs in the concentration, and that's the number of decimal places that you have for the pH. So for example, if I have 4.2 times 10 to the negative 10 molar H plus ions, that has two significant figures. So when I take the calculation to calculate pH, I get 9.38, has two decimal places. Okay? So pH can actually be measured experimentally a couple different methods. We talk a lot about pH meters. These take rapid, accurate pH readings and read these out digitally in real time. So this kind of can get you something that we're going to talk about with some of our titrations. You can get what's called a titration curve, which shows the pH change over the span of an experiment. You can use acid-base indicators like some of the ones that we're going to use. Each indicator, though, has a very specific pH range that it works in and a very specific color change to be seen. So if you're going to be using an indicator, you often have to know a little bit more about your experiment than if you were using a pH meter, because you have to know the correct range to be in, and you have to know what to look for. Or you can use pH paper, like litmus paper, and these operate the same like the acid-base indicators, but instead of having to test the whole solution and placing an indicator in there and it changes the whole color of the solution, you can test small samples on a piece of paper that's going to have the same color change. Again, these you kind of have to know. If you want to know specifics about pH, you have to know what kind of paper to use. Some paper, litmus paper, just tells you whether it's acidic or basic, doesn't really tell you how much. So if you want to know exactly the pH, your best bet is going to be a pH meter, but that requires a lab to operate it in or some sort of setup to be able to do that. So pH indicators and pH paper are often used. Okay, so we're going to be talking a lot about this week and getting to do some titrations of our own. So come prepared tomorrow.